Hello everyone. So we have a cantilever beam of a rectangular cross-section and it is subjected to a shear force V as shown in the figure below here. So now we're given that the bending stress is given by sigma x, which is equal to m times z divided by I, where I is the moment of inertia. Now we're also given that m is equal to negative v times L minus x, and we're told to assume a state of plane stress parallel to the xz plane. Now essentially what this means is that sigma y and tau xy as well as tau yz are going to be equal to 0. And now our goal is to find the transverse shear stress tau xz by integrating the equilibrium equations over the beam thickness and applying the boundary conditions where tau xz is equal to 0 at z equal to plus minus h divided by 2. Now, we are given the equilibrium equation found here, and we're also given the adaptation, where the partial derivative of tau xz with respect to z is equal to negative of the partial derivative of essentially sigma x divided by the partial derivative of x. And that's going to be equal to negative z divided by our moment of inertia times essentially del m over del x. So now we're going to start out by writing that relation there where we have partial of tau xz with respect to z is going to be equal to negative z divided by I times partial m partial x. Now we're given the equation for m, and what we can do is we can take the partial derivative with respect to x so that we can replace this term here. So they tell us that m is equal to negative v times L minus x. And if we take the partial derivative of m with respect to x, then we are left with simply v. So now we can make that substitution. So now, after making that substitution, we are left with negative v divided by I all times z. So now what we can do is we can integrate. So if we integrate, or essentially multiply partial z here over to the other side, and we integrate both sides, we're then left with tau xz is equal to negative v divided by 2I z squared plus some constant c. So now, the way we can get rid of this constant c is they actually give us the boundary equation, which we can check to. So with tau xz equal to 0 and z equal to plus minus h divided by 2, what we can say is we can essentially replace these values. So tau xz is going to be equal to 0, and we can say that will be equal to negative v divided by 2I all times h divided by 2 squared plus c. Now here it doesn't matter if we use negative h divided by 2 or positive h divided by 2 because we have that square no matter what, so it works for both cases. And then simplifying this out, we get that our constant c is equal to v times h squared divided by 8 times I. So now we can replace c. So we get tau xz is equal to negative v divided by 2I times z squared plus the constant c, which was v times h squared divided by 8I. And now here, I is our moment of inertia, which for a beam of this structure, I is going to be equal to b times h cubed divided by 12. So in the end, we get a tau xz equal to 3v divided by 2b h cubed times h squared minus 4 times z squared. And we are done.